how do we think very holistically about AI risk, right? Like AI risk comes from very different parts of like how you build AI applications. And then how do we think very holistically about, how we can kind of like set that up and make sure that we're kind of like tracking and managing that well. Awesome. So before we start, just a little bit about me. I'm Shreya. I'm the founder and CEO of Guardrails AI. Before this, I've been in machine learning my whole life. I did a lot of research, and then I worked in machine learning for self-driving cars, and then, led ML infra for an MLOps company before kind of like starting Guardrails. A little bit about Guardrails. So Swix kind of set this up already, but we're the #1 open source Gen AI Guardrails framework. We're used by a bunch of folks, including like these ones here, amongst amongst other companies. Awesome. So let's get started. This is, you guys are at this conference, right? So this is not a surprise to you, where AI agents are really exciting, really amazing, but they fail all the time, right? And that kind of like limits how much we can deploy them in production and what kind of like problems we can use them for, right? This is actually a headline from today. I don't know how many people have seen this, but so Cursor's customer support bot basically made an AI policy. Very candidly, I don't think this is a deal breaker, right? Like, I think this is like fundamentally really thrilling and exciting technology. And, these are like road bumps along the way, right? But these road bumps do limit how effectively, how broadly we can deploy this technology. And so, my talk is going to be about like, how do we kind of like think about how we build these AI applications kind of from the ground up so that, we're designing to, limit these road bumps as much as possible. How many folks are ML practitioners here in the audience? Okay. So this should be pretty familiar, right? So a lot of us have been doing machine learning forever, and then this is kind of what doing ML looked like, right? You start by, creating a data set, you define a metric, accuracy, F1 score, whatever it is that you're kind of chasing. You train your model, build your model, and then you do a bunch of eval before you finally kind of like push to production, right? And this is like really straightforward cookie cutter. This should be pretty familiar, where, this was kind of like the glory days of confusion matrices, right? Like this was so essential to how we did work and how we thought about, how we're making progress, et cetera. And, if we have like all of these greens in the diagonal, then we're good, right? And that is what AI development or ML development look like. Cut to today, where you are now evaluating these two things, right? You're comparing like these two completely unstructured answers, and then how do you really map this idea of, this diagonal, confusion matrix to something like this, right? It just kind of like really upends a lot of like how we, upsets a lot of how we think about, AI systems. And I think like it's pretty fascinating to think about like, it's still like our titles might still be the same, right? And actually, it might have changed from ML engineer to AI engineer. But why does so much of like what we know to be true about how to build these systems, like why has that changed, right? And so this talk is really like investigating a lot of these truths that we knew from the past. What fundamentally changed about these truths, and then how can we update our process, right? So that we're still in the green and we're not, building these systems that are like very brittle. So first of all, like finite labels, when we were doing machine learning in the past, the reason why we were able to build these confusion matrices, a lot of our, like labels or predictions look like, dog or cat or stop sign if you're in self-driving cars, right? It's just a fundamentally easier problem than looking at something like this and trying to estimate, like, is this good or bad? A deterministic code path, same input leads to same output forever. A finite input surface, even if, I used to work in computer vision, which is at that point was like the highest dimension that your AI inputs could be. And, even then it was like a fixed pixel grid. If a lot of, ML was really like data science, and, that really meant like tabular rows, which are again, like very, very easy to track. Now you can have, like million context length inputs, right? Like how do you kind of like reconcile the two? A very knowable data distribution. So even if you were putting into production and you had like a test time distribution, it was still easy to kind of like estimate or plot what the distribution was, right? Maybe it would surprise you, but it was still knowable in process. And then the metric would line up with the spec. Let's say you were chasing like accuracy or F1. That was literally often very aligned with like what your business goals were. And then metrics were also trivial to compute, right? So for example, like counts or hits and misses or intersection over unions, if you're doing, like something more complicated, right? So you didn't have to think about like, okay, how do I even reason about like, is this something that's good or bad? And so, coming to like what I'm going to be talking about in this talk, which is like 3 concrete ways that a bunch of these assumptions get broken when we talk about, the 2015 AI playbook. All right, first of all, how many of you kind of like, I have this question actually for the audience, which is like, how many of you use accuracy when you're talking about, the AI systems that you're building? And then 2, if hopefully people at the back can also look at the deck, do you have a preference for like which of these 2 answers is more accurate, compared to the other? I'll give you maybe like 10 seconds to read it because I know it's a finite time slot, but after 10 seconds, maybe let's get a show of hands for answer 1. How many people think answer 1 is more accurate? Okay, we have Swix and then a sprinkle of people over here. And then for answer 2, how many people think answer 2 is more accurate? Okay, another sprinkle of people over here. I'd say it's pretty tied. Now, interestingly, both of these answers have the exact same facts, right? So what you guys are really responding to is, the tone, the verbosity, the density of the facts per, per unit of text, etc., right? So this idea of like accuracy kind of like really gets broken down when you kind of like think of this like really high dimensional space, right? So rather than thinking about accuracy from, this like classic scalar metric, a better framing of it is, in terms of like this vector, where you really think about breaking down like what accuracy really means to you, right? So for example, like comparing these 2 answers, I actually break it down into these, for example, for this specific question, it was, these 5 metrics: factuality, safety, tone, helpfulness, and latency. And then really kind of like marking each individual one on, how it kind of like performs, right? So this tells me like, each answer is like better on one, worse on the other. But I think the core idea to kind of like take from this is that chasing one metric, which is historically how we've done ML engineering, right, doesn't translate well to AI engineering, where like quality rather than accuracy is the thing to chase, and quality is like very multidimensional. Making things much, much worse is the problem that it's very hard to even start computing these metrics. So when I talk about like factuality, how do you even establish what factuality means, right? Or safety, how many people here can define what AI safety really means in the context of this, customer support chatbot or this model? Tone alignment, latency, etc. might be easier, but we're also in this like now regime where it becomes like really, really challenging to, think about like not just what am I really improving when I'm building an AI system, but how do I compute that I'm actually improving that, right? And it's this 2-tier problem, which is like pretty hard. Awesome. Problem number 2 that really, again, upsets this whole playbook that we had, which is that static tests fall apart. For example, I'm sure this is like very familiar to most people. I've been doing ML for a while, where in 2018, everybody would talk about, I think why am I blanking on his name? Sorry, I think a bunch of like ML folks would really talk about, how ML engineering is really like 90% data engineering and 10% of it is like really building the models. And we used to invest like all of this, insane amount of time making sure that our data is really well curated, right? And then once we had that, we'd use like sklearn or whatever and really kind of like optimize it on the data set that we'd kind of created. Now, when you come to the Gen AI regime, that way of thinking about, how to build ML applications kind of like really falls apart, because when you think about this like static, really high quality curated data set, it tends to be like very, very, finite compared to this infinite space that your AI system can really kind of like, respond to or surface, right? So I like to think of it as this like iceberg where if you have like a golden data set, which is typically how most people today do AI engineering, maybe you'll have like 1,000 examples in it, right? Where you've painstakingly gone in and like curated and labeled those examples. Whereas like when you actually ship something like this into production, you'd end up with like, again, I'm happy to talk through like how I came up with this like really ballpark way to kind of quantify this number, but like 10 to the 100 possibilities of what your input space can look like, from like niche domain questions, multi-turn, like weird multi-turn interactions, adversarial jailbreaks, etc., right? So how do you like start to kind of like square this away between like you're only testing on this like finite thing, which worked in, the ML world because your distribution was knowable and you could match your expected distribution, and your finite curated data set. But even like plotting the distribution of your inputs for Gen AI is really challenging. And so, it becomes really, really hard to test it with a static data set, right? If you also like actually try to reason about how much data do you really need to evaluate your AI system on in order to kind of like detect and catch these like really long tail edge case errors. Let's assume that you expect your AI system to hallucinate like 1 in 1,000 times, right? For actually testing, for actually like seeing this in practice with maybe more than a 99.99% like likelihood, you will need to kind of like test your AI system on about like roughly around like 9,000 or close to, let's say, rounding up like 10,000 prompts here, right? Now those 10,000 prompts, because it's so hard to again like calculate them, measure them, etc., will need to be kind of like manually poured over to see where the hallucination happens and kind of where it occurs, right? And that becomes like, yeah, again, really, really challenging and really hard to track. And this is a tractable error. This isn't even something I'd consider like a true blue edge case, right? Awesome. And then like the crack number 3 that really breaks our ML playbook is that deployment isn't the finish line anymore. So I have this example here, and this is if you've deployed an AI system, this might have happened to you. If not, I talk to, for example, like execs at enterprises every day, right? And this is literally like the top thing that's in their mind that's like really limiting AI progress, which is that let's say we do a bunch of internal testing, and at 9 a.m. all tests are green, and then we ship the system, right? At 10 a.m. a power user comes on, like breaks their system, and then 12 p.m. there's a screenshot posted on like r/chatgpt talking about like how horrible whatever, or how stupid this AI system is and how it kind of get something wrong, and then the media picks it up, right? Kind of what happened with the cursor example, honestly, that I was showing at the beginning of this talk. But it's this like weird regime again where, because you don't have like any runtime verification, every new prompt is basically this like 0-day kind of like, vulnerability. And again, contrasting this with like deterministic ML, right? Deterministic ML basically stays fixed after deployment, so you're able to kind of, again, anticipate the distribution and test it, whereas like generative AI, keeps fielding all of these like unseen inputs forever. All right, so we talked about the problem. Now, as we start thinking about the solution, this is basically going to be the rest of my talk, which is the 3 things that we can do to kind of like update the traditional ML playbook from 2015 to the AI playbook from 2025, And to be fair, there's a bunch of other things you can do. You really should think about, how to design good like human in the loop, how to design good UX. I think like all of those things are more important now than ever. Deployment and scalability, especially on like these really large GPUs with massive models, again, is really important. But these are, the 3 low-lift things that you can do as you're thinking about, like what to consider or what considerations you should have for your AI system. The first is, accuracy doesn't map to quality anymore. So when you're thinking about the metrics to chase, really chase, like vector-based metrics rather than scalar metrics. The second one is around like static data sets. So again, golden data sets, curated data sets, it's how ML has been done forever. But because of the infinite input space that a lot of these systems can have, we really need to, come up with like a tractable way to move to like dynamic data sets in a way that we're able to catch these like edge cases, these long tail scenarios. And then finally, instead of shipping without inline guardrails, really thinking about like production or deployment as like a loop rather than a once-off, gate, so that we're constantly monitoring, detecting, and fielding where errors occur, and then feeding that back into our system so that we can have a continuously improving system. I think those are kind of like the 3 key ways that our thinking needs to kind of like change about how to build AI systems, right? Awesome. So first thing, scalar to vector metrics. First of all, I think this is, I talk about this a lot, which is, ML engineers really need to kind of like start thinking like product managers a little bit, and then ML engineers kind of hate this. But you'd be surprised with like how many people I talk to that have applications that they've built out that are close to getting completed, and it's very hard for them to make a business case about why this application is like good enough, right? Again, every exec, every like leadership person that you talk to is going to have these questions about like, how do I know that this isn't going to get me in the headlines the next day after I deploy it? And then as you're answering that, really having like some sort of taxonomy or some sort of like grounding of how you think about these metrics, right, ends up becoming really key. So in general, there's a bunch of like systems for thinking about metrics that I highly recommend. I think the 4 big categories I typically see, one is around like correctness metrics. So this is the way to think about your application where, without this, your AI system is unusable. So this could be around like factuality, language adherence, appropriate human handoff if you have like a human in the loop like system, right? And so you typically like think about, sitting down with stakeholders and defining what each of those looks like, and then making sure that you're able to, concretely measure that, right? And have some automated system about measuring that. The second ends up being like, product level metrics. So these are typically ones that don't impact functionality, but do impact product retention, stickiness, et cetera, and, will make sure that your users are going to come back. So tone alignment, intent understanding of your users coming to the system, et cetera. Why this is a metric now for ML when it wasn't in the past is because, it's very hard to kind of like evaluate or even quantify what the tone of an answer is, right? So your product teams, your stakeholders are going to come to you as the ML practitioners to kind of develop some automated way of like detecting what that tone is. Safety, security metrics, again, this is kind of like our bread and butter. So this doesn't really impact the functionality of what you're building, but often, especially if you're in a larger enterprise or if you have, any amount of like brand risk, et cetera, this will end up being a blocker from actually shipping your system from, your legal and compliance teams or from your responsible AI teams, right? So this really relates to metrics around jailbreaking, off-topic risks, et cetera. And then the fourth one, and this is, really an emerging standard for what duty of care you need to kind of like adhere to as you're deploying AI systems, right? And so aligning yourself well with these metrics is just kind of like good practice and kind of like future-proofs what you're building. So NIST, AI-RMF, OWASP top 10 for LM, ISO, for 2021, et cetera, like all good kind of like practices, right? And then the kind of like I've listed out here like a repeatable process for implementing a bunch of these metrics. So the first is, like checking for standard implementations. Before you kind of like start building an LLM as a judge or anything, just check whether regex, blue, BERT score, et cetera, would suffice. I think LLMs have become so easy to use now that I often meet with people that are using LLMs because, they don't want to write maybe like 20 lines of code. And then, especially if you care about reliability, latency, et cetera, really do write those 20 lines of code. It's going to be worth it. If you don't have that, starting out with, seeding with like 3 to 5 gold examples where, you with like maybe another person working on the project with you really writes out like a rubric of what you care about and manually creates or curates, those like 3 to 5 examples. And this number, like 100, is kind of like ballpark here. This will really vary based on what you care about. 50 is often sufficient, et cetera. But, you want to kind of like curate like, you want to create a way of automatically testing for this metric. And as you're doing that, you want to make sure that whatever automated way you have aligns well within some threshold with, with what your rubric or your criteria is. And so that's where this like scaled up kind of testing comes in. So call in SMEs if you need to, like set thresholds for disagreement. If any of you are familiar with, like HCI work or like crowdsourcing research, et cetera, in the past, a lot of it kind of translates really well to, like the modern AI development domain. Then finally, like LLM as a judge gating. So make sure that, you have some kind of threshold for how much alignment you want between, the LLM as a judge versus the human kind of like scoring. I think often like having some threshold here is important, but also there's little like tips and tricks you can do. For example, like using structured data ends up, leading to like more kind of like reliable way of getting these metrics. And so, you can kind of like adopt all of those to make sure that you're getting like good outputs. And then finally, manage judge volatility. Does this judge provide consistent judgment? So fine tune if necessary. Before that, don't fine tune. And then I tend to stay away from a lot of like these really jargony things, but like there's this idea of a council of judges, which is really just like ensembling, if you're familiar with it, right? You're just really using a bunch of different LLMs set up in different ways, and then if you and certain conditions is like when you kind of predict a certain output, et cetera, right? Okay, second one, static to dynamic data sets. So the important thing here, and evals, it's such a hot button topic, right? Like all of us have opinions on eval. We've been hearing about evals forever. But I think like the fascinating thing about eval is that there's no one single process, or there's no like one-stop shop, to kind of like solve evals in some way. So the most successful process I've seen from the most sophisticated teams that I've kind of worked with is this layered eval approach, where you're really like layering in a bunch of these techniques to make sure that you're able to get very good coverage over the types of failures that you might end up seeing, but you're still able to kind of manage scale, right? So again, coming back to this problem that we talked about, where if something has 10 to the -4 likelihood of failure, and you want to make sure that in your system you want to catch it with like more than 4 nines of confidence, you will have to evaluate 10,000 prompts. And because these prompts are hard to evaluate, you will have to typically manually pour over those 10,000 prompts. So this is where having those like automated evals can be helpful. But really going through this like layered eval approach is often like the best, most tractable way to solve this problem. And so this ladder that I've seen a lot of these successful teams adopt is this 4-part process. So in the first couple of parts are really about, in this baseline setting you want to do well. So at this point, you're not really caring about, like this number. You're really caring about for your average user, how do you end up kind of performing? And then the next parts of it are about, for an adversarial or malicious user, how does your system kind of like update, right? So the first couple of ones are, for synthetic testing. This is where you can generate like millions of low-cost auto-generated prompts. And you can use those prompts on your system and then kind of see how your system performs. Again, having those automated evals that we kind of set up in the previous step ends up being key to meaningfully have like traction in this step. Curated golden data set. Again, most of the teams I talk to, this is the only thing that they're really doing. But this is, again, one of the 4 parts of the steps that I've seen, be successful. This is where you have like very high signal and then version controlled examples, and a human has kind of sat down and curated them. Targeted human review. This is, where either with an internal team or with an external crowd that you hire, you just let them loose almost on your system. And this is where you're going to start to see some of those out of distribution examples that violate implicit assumptions that you made while creating that application, and then you're able to kind of test and see how your application performs, right? And then finally, external red teaming. I know people think about red teaming and EVA as like separate things, but I really think it's all part of the same process, where you're kind of like trying to understand how correct or effective your application really is, where you're really looking at adversarial experts doing like periodic sweeps, right? So they're trying to see like what is the worst that the system can really be, and if that worst is better than your acceptability threshold, like that again gives you a lot of confidence, right? So I think like one of the big things I see people kind of struggling with a lot is like, how do you really inspect this long tail? Where again, you're looking to surface this like really long tail edge cases, that you won't typically run into if you have like 1,000 data set examples, right? But because of how complex the data set modality is, you also don't want to look at 10,000 examples to really find them. And even then you'd maybe find like one, for example, right? Like that's not really tractable. And so how do you like really solve this problem without, manually going through or poring over all of these examples? And this is, I think, like a big challenge. And we're actually kind of like, if this is something that, really resonates with you, come find me maybe after the talk. We have some like experiments that we're doing in this area, which are, early and exciting. And I'm happy to, kind of like share what we're kind of like seeing there as well. And then finally, changing your pattern for deployment from a gate to a loop, right? Where you're doing constant monitoring, constant kind of like mitigation of live risks that you see, and then feeding that information back into your system so that you're able to update, your metrics, your like data sets, etc. really is, essential. I think it was talked about as well in the ML world, like we talk about data drift, etc. right? But that would be your underlying distribution is shifting. I think now we're kind of, again, operating in this space where the distribution is unknowable. And so it's really important to kind of, have this like continuous verification of your assumptions, essentially. So this is where guardrails come in. Swix kind of set this up well, but 2 years ago, I'd be, going deep into this. 2 years later, I'm guessing a lot of you are familiar with this. Can I, again, get a show of hands how many people know what guardrails are or how they work, etc.? Okay, So a lot of the room. So I'm going to skip over this. I think core assumption is that rather than using your LLM raw, make sure you're validating and verifying all of those implicit assumptions, especially the ones that, are going to land you in some sort of regulatory or product or functionality or usability kind of like mess, right? Make sure you have like explicit verification of like all of those assumptions, essentially. We kind of see this pattern evolve from the start, where it was like much more centered around AI applications, to now being really targeted to AI platforms that companies are building. So we see like guardrails, for example, like live around centralized proxy, so that every single request that goes through your organization is guardrailed and protected and safe, and you're not leaking any PII, for example. And then you can also kind of like see you can kind of like pick and choose which guardrails you really want, and then add them to the application that you care about. So how do guardrails really work under the hood? We kind of like, a lot of people I talk to have this assumption that, okay, this is all like LLM as a judge or LLM verification, right? But guardrails, even though the word might be newer when it comes to AI, but the concept is really, again, ensembling, right? And kind of like building these cascades of systems that go from like latency, that basically manage your cost and kind of like correctness trade-off. So really having different methods from your underlying system that you use for verification is generally good practice, right? So we see kind of like these three core ones, where it's rules or heuristic systems, small fine-tuned ML models, or secondary LLM calls. And I have some notes here about like what types of like verification they're really good for. But more often than not, you end up coming up with like a combination or a cascade of these approaches, right? And the more you kind of like mix and match, and you have like independent kind of like ensembles with a lot of different kind of like overlapping properties, the more I guess like tight knit your application really tends to be. This kind of goes without saying, but we're really fighting fire with fire here in some sense, right? Like it's guardrails are also ML models at the end of the day. And so, by definition, like not all guardrails are really created equal. So some of the things that we've done, we've launched publicly, and I really urge you to think about when you think about, adding these like risk mitigation systems to your AI applications, is like benchmarking them, right? So I find people like add, a lot of, for example, like PII guardrails without really like nobody thinks really about like evaluating guardrails, which again is kind of like surprising or shocking to me. So we launched this like benchmark, for example, that looks at how effective guardrails are across PII detection, right? And we basically kind of like compared this across a bunch of models. So this one, for example, Microsoft Presidio. I'm a huge fan of the framework from like a usability perspective, but in terms of performance, it leaves a lot of room to be desired, and it really is. I'm kind of surprised by like. Well, I'm not surprised by it. I think it's been around for a while. It's very easy to use. But people use Microsoft Presidio a lot. And I think they're very explicit about the fact that they don't release benchmark numbers for it in terms of, accuracy or F1 scores, etc. So some of the work that we did while, helping folks think about what guardrails they really want are, releasing a benchmark in a data set where you can kind of evaluate a bunch of this for accuracy, latency, etc. And, we kind of found that like, we tried to kind of build the best of both worlds here, where Microsoft Presidio, which is primarily a rules-based system, kind of like ensembles with, transformer-based models for detecting like sensitive information or PII. And we kind of found that we're able to outperform a lot of those systems. Granted, they need a GPU to deploy. But if PII is important enough for you, where, it's a blocker to launch, or it's a blocker from actually being able to use the application, then you're probably okay with like using that GPU, right? And you get like maybe a 4x increase in latency, but it's still like 64 milliseconds as opposed to 15. And so still, smaller than or faster than human perception. We did this for jailbreaking as well, where we kind of saw, jailbreaking, again, classic LLM security or safety problem that a lot of people worry about. And again, is one of those categories that often ends up being like a launch blocker. And again, we kind of found that some surprising results here. So specifically, we found that Llama Prompt Guard, which is again a very commonly, popularly used, framework for this, actually ends up being like, too, too generous, I guess, in terms of, like classifying everything as like a true positive, where even if you were to use like Anthropic with the right kind of system prompt, etc. And Anthropic actually has a pretty cool blog post about this. You'd end up with like higher, like true positive rate, etc., which is, a more kind of higher F1 and then a higher true positive rate, which is, like typically what you want to optimize. Ends up being like much slower. As you can see, LLMs, they're great, but they're slow. So, you can kind of like think about other models, but really do benchmark and validate like everything that you're using, any ML component that you're adding to your system, right? Awesome. So my main kind of like takeaways for all of this, a lot of like the language that we're using for building these same systems kind of like translates over, but a lot of the processes, etc., are very broken compared to what we had before, right? And so there's a lot of things we need to update and learn, and we're constantly evolving in terms of how to build more reliable, more robust AI systems. But the three, key ones that we can adopt today that I feel like are pretty low lift in terms of how we think about these systems are metrics, thinking about, like vector versus scalar metrics, and then aligning, creating these automated metrics that align well with how we think about, correctness or quality, right? Testing, going to dynamic testing from static testing, again, really critical and is essential for, avoiding a lot of these common failure modes that we see in headlines, for example, all the time. And then finally, thinking about deployment as like a continuous loop rather than a one-time gate, again, is a new, paradigm that's kind of like essential when you think about like AI deployment, right? All right. I think that's my talk. Happy to answer any questions that folks have, or and I have this like QR code here that I think it's basically just my LinkedIn, where you can kind of connect with me if you want. I think that's my talk. Happy to